Hello, thanks for joining me. This is the lecture for linear algebra, Math 2860, for Friday, October 17th. Sorry, I had to cancel class. I had a problem with my knee, so I'll be okay, but I might not be able to get around very easily. So next week, we'll probably either have some Zoom classes or I might find a substitute. I'm not sure which one you would prefer. I know you probably don't want to go back to the pandemic situation where classes are on Zoom, but I'll make sure I get back on campus as soon as I can. All right, so last time we were talking about, near the end of class, we were talking about the conditions that we called closure under addition and closure under scalar multiplication. And these are both properties of a set. Let me write them both down. Closure under addition and closure under scalar multiplication. And these are properties of a set. So imagine you have a set. So if S is any set, of course you could call the set anything, but I'm just calling it S, where we know we can add the objects in the set. Sometimes those objects are just going to be generally called vectors. We know how to add the objects in the set. Let me write that a little better. We can add objects in the set together. And a set where we know how to multiply objects in the set by scalars. Remember, in this class, a scalar is just a real number. Okay, we'll generally call our scalars k, and k can be any real number. So if you have a set where you know how to do those things, examples would be sets of numbers or sets of vectors, since we took some time to figure out how to add vectors together. Sets of matrices, because we know how to add matrices together, and we know how to multiply matrices by scalars. Those are all potential examples of sets that we could ask ourselves, do they satisfy these two axioms, closure under addition and closure under scalar multiplication? Okay, so I gave you some examples last time, right? So last time, near the end of class, we had an example, maybe we'll let S equal all even numbers. So you might not be sure exactly what the definition of an even number is, but let's just say so S would equal the set of numbers like 2, 4, 6, 8. But it also, by the way, it also includes, you might not think of it this way, but it also includes the number 0. I really shouldn't put them in that order though, right? I should do ... and 0, -2, -4, etc. So it really goes infinitely, in both directions. Positive and negative even numbers. 0 is an even number. To be even, it simply means that when you divide it by 2, you have a remainder of 0. Okay, so I think we all agreed. We asked, the question was, A, is S a set that is closed under addition? So we're asking if it satisfies that axiom. I'll zoom out here. We're asking about this axiom right here. Is this set S closed under addition? And we all agreed it was. And why is that? What was our reasoning? Because no matter what, this is the condition I think I wrote on the board last time. To be closed under addition, it means that if we add any two things in the set, I'm saying things because they might be different types of objects. Sometimes they'll be vectors, sometimes they'll be matrices. They could even be functions, like polynomials. If we add two things in the set, the result has to always be in that same set. That's not always true, right? But in this case it is. Because if we add two even numbers, it's just kind of a fact of just the way numbers work. If you add two even numbers, you always get an even. That's probably something you you learned a long time ago. You can try a bunch of examples. 4 plus 6 is 10. They're always going to be even. That's really because if you're adding together two things that can be divided by 2, their sum is also divisible by 2. Okay, so yes, it is. So this set of all even numbers could be a vector space. To be a vector space, it has to satisfy both the closure axioms, not only closed under scalar or under addition, it has to also be closed under scalar multiplication. So let's ask that one next. Is S, the set of all even numbers, is that set closed under scalar multiplication? And it turns out, this one, we haven't done an example of this yet, but let me explain it. It has to be, in order to be closed under scalar multiplication, let me add a note here. I can change colors. In order for that to be true, it has to say that if we multiply an object in the set, or a thing in the set, it has to be the case that, or I should say we multiply it, I have to say what we're multiplying by, right? Multiply by any scalar, any possible scalar, k. The scalar could be any real number. It doesn't have to be one of the numbers in the set S. It can be any real number, positive, negative, a fraction, a decimal. It could be irrational, like square root of 2 or pi. And so in order to be closed under scalar multiplication, the set has to satisfy the property that if we multiply any object, I really should say this, any object in the set by any scalar, k, the result, when you do that scalar multiplication, must always be in the set. Must always be in the set. So in other words, you can't scale or multiply your way out of the set. And just to recap, closure under addition means you can't add your way out of the set. All right, so let's apply that criteria here for the set of all even numbers. Does that satisfy closure under scalar multiplication? Well, let's try a few. Let's choose some elements from S. Well, let's choose, 6, for example. Take 6. Is it always the case if I multiply 6 by any scalar, I land back in S? Well, here are some scalars that I'm allowed to multiply by. Of course, I could multiply 6 by 2, or I could multiply 6 by 0, but I could also multiply it by 1/2. That's allowed, because it has to work for any scalar. I could also multiply it by pi, or negative, 23.1. Okay, I have to try if it's always going to land back in S when I multiply, then it'll be closed under scalar multiplication. Well, of course, 6 times 2 is 12. That's in S. So that one's okay. 6 times 0 is 0. That's also in S. So that one's okay. But check it out. 6 times 1/2 is 3. 3 is not in S. And it's also not going to work for the others. It's also going to not work for the others that I've listed here. Certainly 6 times pi is not an even number. 6 times negative 23.1 is not an even number. So since it's not always an even number, it's not always in S, the answer is no. This set, S, even though it's closed under addition, it's not closed under scalar multiplication. Okay, so by the way, so the conclusion is, S is not a vector space. It has to pass both axioms, and actually some other axioms as well, but these are the only two that we're really worrying about in order to be a vector space, so it's not going to be a vector space. Okay, so we're in a chapter 4 in the book, and the title of that chapter is Vector Spaces. So that's what we're studying right now. Okay, the material is a little abstract here, but I'll try to break it down, make it simple for you. Let's do some more examples. Okay, so maybe our next example, I don't think I got to this last time. How about this? Maybe I'll call it something different. How about T is the set of all even numbers. Sorry, we just did even. I meant to switch it. All odd numbers. And I'll ask the same two questions. Is T, A, B, is T closed under addition? Should probably come up with an abbreviation for that. so we don't have to write so much. And then the second one is T closed, we'll just use CL for closed, under scalar multiplication, so I don't have to write it all out. All right, so again, we're asked the same two questions. Just think about it. You can either write some things down, and a lot of these are just basic logic. Take any two things in T, odd numbers, right? So things like 1, 3, 5. If you add them together, in order to be closed under addition, it would have to be the case that whenever you add odd numbers together, you have to get another odd number, because you have to land back in the set T. Well, what do you think? I think it's pretty clear, right? If I take 3 plus 5, right? 3 plus 5 equals 8, which is not odd. So the first thing we tried failed. I think they'll all fail, actually. So no, it only needs to fail once for it to be no. and I think they all actually fail. So this is not closed under addition. And so of course it's not a vector space. But just to be curious, let's check the second closure axiom, or the closure condition. Is it closed under scalar multiplication? That's also no, right? If I take 5 and multiply by even just 2, I get 10, which is not odd. But I also could have multiplied it by a half or pi or something. So it's neither. So this one passes neither of the axioms. Okay, and if we want to do some examples, let's do some more examples. In fact, how about this? Let's start with examples of well-known or famous vector spaces. These are examples that are sort of the big class of examples that people think of. A lot of people think of when they hear or talk about vector spaces. So the first example is just the set of all real numbers. It's not nearly as an interesting of a example as something like if I ask about the set of all even numbers. The set of all even numbers did not end up being a vector space, but it was more interesting to think about. But the set of all real numbers it's almost obviously a vector space. So think about this: if you take any two real numbers and add them together, you always get another real number. So since the set of real numbers already contains all real numbers, there's no way to add yourself out of the set. So it's closed under addition. Closed under addition. And then what about scalar multiplication? Well, if I take any real number, any number at all, and multiply by any scalar, that's really just multiplying two real numbers together. When you multiply two real numbers together, you get another real number. Since our set contains all real numbers, it must be an element in that same set. So it's closed under scalar multiplication. Okay, it passes both of those. There are actually, I've been calling these axioms sometimes because these are requirements for a set to be a vector space. It turns out there's actually 8 other axioms to be a vector space. Things like it has to have a 0 element, it has to have negatives for everything that's in there, and a variety of others. But we won't focus on those. This is really just an introduction to the material. We'll just focus on these two. Any questions that we get on a test or anything, we'll focus on these conditions. All right, so how about this? It turns out not only r, but as another example, what about maybe, how about r squared? What do we mean by r squared? That's all two-dimensional vectors. Okay, that's what we call r squared. That funny-looking r is the set of all real numbers. When you have an r with a 2 as its exponent, that's basically saying you have two real numbers put together. So examples of that would be things like, anything that I could write as AB, a two-dimensional vector, where A and B are just any real numbers or scalars. All right, so is this also a vector space? It is. Why? Think about the two closure axioms. If I add any two-dimensional vectors, I'm going to get another two-dimensional vector. So it's also closed under addition. And if I multiply, so just, a few examples, right? If I take any two-dimensional vector, like -2, 5, And just add it to anything else. I'll just make some up, like 3, 7. Well, if I add those up, what do I get? Negative 2 plus 3 is 1, and 5 plus 7 is 12. No matter what 2 you have, the result is just another vector of 2 dimensions. There's no way you can add yourself out of the set. So it's closed inner addition. And then, as an example, if I take any 2-dimensional vector, like negative 2, 5, and multiply by any scalar, doesn't matter what I put here, a half, I could put any other scalar there, like pi or whatever. What would this be? This would just be negative 1 and 2.5. Again, another vector in R2. So I can't scalar multiply my way out of the set, just like I couldn't add my way out of the set. So it passes both. It passes both of the we call those closure axioms. Closure under addition and closure under scalar multiplication. Okay, well, you might think there's actually not much of a there's nothing special about R2. What about R3? R3 is a set of all let me write that 3 a little bit. R3 is a set of all, in set notation, is a set of all A, B, C, all 3-dimensional vectors, where A, B, and C are real numbers, right? That's really what R3 is. Well, it's the same idea as R2. If I add 2 3-dimensional vectors together, I get another 3-dimensional vector. So since our set contains all of them, it must be in there, so it's closed inner addition. And also, if I multiply any 3-dimensional vector by any scalar, I get another 3-dimensional vector. Okay, so in fact, how about this? Sorry about that. Let's it turns out, why don't we just use as our 4th example, I don't have to keep telling you different powers of R, let's just do Rn. In other words, this equals the set of all n-dimensional vectors, where n could be any positive whole number. This is always a vector space. It's one of our famous examples. So really R2 and R3 and R are special cases of this family. It's like a family of vector spaces. All right, how about this? Let's do some more examples that are not just vectors, traditional vectors. So how about this example, number 5? How about this? All 2x2 matrices. If you think about it, can we add? So let's think. This set. By the way, this set has a name. It's called M2, 2. Or some people actually use that R notation again, but they just write 2x2 as the exponent to indicate that it's real numbers, right? A, B, C, D, where A, B, C, and D can be any real numbers. So they have an arrangement of real numbers in a 2x2 pattern. That's why they use that notation. So you could either describe this set as M for matrices, and 2 are the rows and columns, or R 2x2. They mean the same thing. This is a vector space. If I take any 2-dimensional vectors that look like this and add them together, we already know you're going to get another 2-dimensional vector. And since our set contains all of them, it's going to be closed inner addition. Same thing for scalar multiplication, right? So if I just add 2-dimensional vectors, I just get another 2x2 matrix. I didn't mean to say vectors, I meant matrices. And if I take any 2x2 matrix and any k, I'm just going to get k. This is A, B, C, D. I'm going to get Ka, Kb, Kc, and Kd, which is just another object or matrix, another matrix that's in M2x2. How do I know it's in there? Because M2x2 has all of them. Okay, so this is another vector space, right? And then again, number 6, it doesn't really matter what size the matrices are, right? The matrices could be 2x2, so they could be 5x5. So M3, 4 is a vector space. So is M 7, 12. That's a vector space. So in general, M, comma n, the set of all M. This is set of all M by n matrices. That's a vector space. Okay, so these are some classic examples. Let me give you at least one more that's somewhat different. How about this? This is kind of interesting. Let P equal the set of all polynomial functions. Okay, so as an example of things that in P would be such as the function, how about let's call this the function f of x equals negative 2x squared plus 3x minus 7. I just made that up. That's just an example of a function that's in P. Maybe think of another polynomial. Polynomial, you probably recognize the form of polynomial. Let's call another one, let's call it G. How about 14x to the third, right, minus 3x plus 2, for example. There's another polynomial. This one's a third degree polynomial because the highest degree is 3. This one's a second degree polynomial. There's no limit on the degree. To be a polynomial, it just has to be terms where it has x's and powers of x and constants. Okay, well, why is this a vector space? Well, do we know how how to handle f of x plus g of x if I took those two functions? Yes, we would. We would just f of I think we write that as f plus g of x would just be the function where I just add these two together. You just add the outputs of the functions together. You might have to combine some like terms, but I guess we'd get 14x cubed minus 2x squared. I'd get plus 3x and minus 3x, so the x's actually disappear, and we get minus 5. But this is just another polynomial. Whenever you add two polynomials, you get another polynomial. Therefore, the set of all polynomials is closed under addition. Closed under addition. And what about multiplying by a scalar? Does it make sense to take k times f of x? Does that make sense? Yes, it does, right? It would just be negative 2k x squared plus 3k x minus 7k. It's just another polynomial. And since P is the set of all polynomials, it must be in that set, and therefore it's closed under scalar multiplication. Okay, so I'm just trying to give you an idea of something. We'll do more of these examples in our next class, which will be next week. Okay, I do have a worksheet for you. Before we do it, let's get to it. Let's do a couple more things. So I'm trying not to make the video too long. I think it's gonna have to be in two parts, right? So my recording stopped for a minute, but that's fine. Let's do a couple more things. So here's a definition. Sometimes you have vector spaces inside other vector spaces. Okay, so if you're familiar with the idea of a subset is a smaller set inside of a larger set. Here's a definition. If V is a vector space, perhaps one of the famous ones we just talked about, and a subset S of V, if that set is, let me change the letter this time. I like to use the letters that the book uses. A subset W of V. If a subset W of V is itself a vector space, then we say that W is a subspace of V. So that word subspace is a combination of the word subset and vector space. If you have one vector space inside of another vector space, it's called a subspace. Okay, we'll do some examples in a second. The cool thing is, in order to be this is actually a theorem that's in the book. It's called the subspace theorem. It says that any subset of a vector space V, which is both closed under addition and closed under scalar multiplication, so if it's got both of the closure conditions that we've been talking about under scalar multiplication, so any subset of a vector space V which is both closed under addition and closed under scalar multiplication is a subspace of V, and that just means it's a vector space itself, and it's just contained inside of another one. Okay, so we're gonna try to do some examples that dive into this, and then that'll be it for this lecture. And there is a worksheet that'll be available on Brightspace. I won't be able to pass it out to you, but you could. Maybe I'll just also email it to the whole class. But you can either get it off Brightspace or to the email I send you. So let's do a couple examples. Okay, a couple examples of this idea. How about this? Let V equal M2, 2. Remember, we just learned what that means. M means matrices, and 2 and 2 mean the size of the matrices. So this is all 2 by 2 matrices where the entries in the matrix could be any real numbers. Okay, and how about this? Let W equal all diagonal 2 by 2 matrices, right? Okay, so this is the problem, and then here's the questions. This would be a reasonable test question. How about this? Write out some examples of the objects in W. That's our first question. All right, so you think about that for a second. It's not very hard. Hopefully you remember what a diagonal matrix is. So let's do that. Maybe you could pause the video and try it yourself. But here's some examples. How about 2, 0, 0, negative 4? That's a diagonal matrix. Remember, a diagonal matrix is any matrix where all the entries that are not on the diagonal are 0. So there's one example. Let's do another example. How about 5, 0, 0, 0? This is also diagonal, because the entries that are not on the diagonal, these two here, must be 0 to be a diagonal. Anything off the diagonal must be 0. You're allowed to have 0 on the diagonal. You just have to have them off the diagonal. In fact, this is a diagonal matrix, the identity matrix. There's a diagonal matrix, and here's another example, the matrix of all zeros. These are all diagonal matrices. Okay, so there's A. By the way, generically, you could write this as A0, 0B, right? That would be a generic form of this set of all diagonal matrices, where A, I guess I should say, where A and B can be any real numbers. Right? That really encapsulates all of them. All right, so question B in this problem. Again, this would be a reasonable. You're going to have a worksheet right after this that like I said, it'll be on Brightspace, or I'll email to you, where you'll get some questions like this. So let's go through this example, and then I'll stop. So the second question is this set is W. Again, W is all diagonal 2 by 2 matrices. Is W closed under addition? If you want, you could pause the video and think about it. But here's a good way to find out. Just take some of the examples that we have in the problem above it, this example or this example or these examples, and try adding them together and just see. Now, this is not a proof, but you'll kind of get an idea what's going on, right? So if I add those two together, what do I get? I get 2 plus 5 is 7. In the upper right corner, I get 0 plus 0 is 0. In the lower left corner, I get 0 again. In the lower right corner, I get negative 4. Is this going to be diagonal? You look at it and you see that it is. And since it's diagonal, since it is diagonal, and W is the set of all diagonal 2 by 2 matrix, it must be in W. So this result is in W. Sorry for the handwriting. So the question is that always going to happen? Is it always going to happen? And the answer is yes. This will always happen, because the entries that you get, if you're adding two matrices that both have a 0 in the lower left corner, you're going to be forced to get a 0 in the lower left corner of their sum. Same thing in the upper right corner. And any matrix that has, any 2 by 2 matrix that has a 0 in the lower left corner, 0 in the upper right corner, must be diagonal. So yes, it is closed under addition. And then question C, is W closed under scalar multiplication? Okay, so let's try it again. Let's take some examples. Here's one of the examples of a diagonal matrix. Put any scalar you want in here. Even pi is a scalar. Is this, let's multiply this out. You'll get 2 pi, 0, 0, and minus 4 pi. But the question is the result still in the set W? Well, how do we know? Is it diagonal? Because W is all diagonal matrices. Yes, it's still diagonal. And that'll always be true, won't it? Because no matter what, when you have a 0 in the lower left and upper right corners, no matter what your scalar is, you're still going to have 0 in those corners, so it'll still be diagonal. Therefore, yes, this set is closed under scalar multiplication. And the very last question, is W a subspace, or is it a vector space, a vector subspace of V? Sorry, V. Remember, in this problem, let me zoom out. V was all 2 by 2 matrices, and W was all diagonal 2 by 2 matrices. Right? Not every 2 by 2 matrix is diagonal, so W is not all of V. W is just a portion of V. But how do we answer this question? Is it a subspace? The theorem tells us if both of the answers to these two questions was yes, then this is yes. If either one of them was no, or both of them was no, then we'd have to say no. All right, let's do one more example, and then I'll stop. And then we'll pick up next week. So last example. Let me zoom in and make it some resolution here. Sorry about that. Last example. How about this? Let again, V is M 2 by 2, same example, but this time let W be all 2 by 2 matrices with a 1 in the upper right corner. Okay? So that's W. All 2 by 2 matrices that have a 1 in the upper right corner. So same 4 questions. A, give me some examples. You might want to think of some or write some down. I'll do that. Here's an example. How about -2, 1, 3, 8? Any 2 by 2 matrix that has a 1 in the upper right corner is going to be an example. Or how about 0, 1, 0, 0? There's another one, right? Or 7, 1, 1/2, 2/3. These are all in W, right? How do we know they're in W? Because W is all matrices that have a 1 in the upper right corner. All 2 by 2 matrices. All right, so question B. Is W closed under addition? You can pause the video and think about it, but here's a good way to check. Just take any 2 things that you got from A and try adding them together and just see what happens. If I take the first one and the second one and I add them together, what do I get? I guess we'll get -2 in the upper left. In the upper right, I'm adding a 1 and a 1, so I'm going to get 2. Lower left is 3 and the lower right is 8. The question is the result always going to be in the set W? Well, not only is it not always going to be in W, in this case, it's not. This one's not in W, right? Why is it not in W? Because the upper W is a set of all 2 by 2 matrices that have a 1 in the upper right corner. Does this matrix have a 1 in the upper right corner? No, it has a 2. So it's not in W, and since it's not in W, we added 2 things in W. We added this and this in W, and we got something that's not in W, which means it failed that condition. It is not closed under addition. Okay, so diagonal 2 by 2 matrices are closed under addition, but matrices of this type with a 1 in the upper right corner are not. What if I ask that, is W closed under scalar multiplication? You might want to think about that one for a second. It's actually not too bad. If I multiply any one of these by any scalar k, as that scalar is not 1, I'm not going to have a 1 in the upper right corner anymore, so it's no. Right? So that was easy to check. And then D, is this set W a vector subspace of the set of 2 by 2 matrices? Well, it's definitely no, because the only way it would be yes is if both of these would have to be yes, and neither of them was yes. Even if one of them was yes and the other was no, I'd still have to say no here. Okay, so that's it for the lecture. try worksheet 12 now. If you have questions, you could send them by email. I'll answer them. If you're really confused, we can jump on Zoom. I can have my office hours in Zoom. So yeah, try that worksheet. It should be in your mailbox. It's also on Brightspace. Submit it on Brightspace, and hopefully it's clear. If you get stuck, just like I said, just send me a quick email. It can be flexible on the due dates and everything. All right, thanks for listening.